So I think we all know this formula. This is Newton's formula, of course. Well, okay, maybe he didn't think about potentials, but anyway, it's essentially Newton's formula. And what we want to do is talk about deriving this formula the way we're doing, the same basic way that we're thinking about the problem at much higher order, the general relativity corrections. So the problem we will work out on the blackboard so you can get a taste of how this works is this. So I made a comment. I said, we don't do Einstein's equation. Anyway, there's Einstein. We don't do that. We don't like Einstein's equation. We like the Feynman diagrams or the scattering amplitude. Well, actually, you'll see we don't even like Feynman diagrams. We like scattering amplitudes, gauge invariant objects. And the information for Newton and all orders in velocity, the relativistic corrections, they're all contained in here. See, there's a coupling kappa. There's Feynman rules of interaction of a point particle with a graviton, which then talks to another point particle. Those point particles are the planet Earth, as far as we're concerned, because we're thinking about interactions of bodies at long distances. So that the distance is much longer than the size of the body, so they're point particles. It could be black holes. Doesn't make any difference. You learned that effective field theory, separation of scales. If there's anything that you should learn from all of our lectures, separation of scales. Once you have the separation of scales, point particles, let's do Feynman diagrams. And the part that's really remarkable is the distance between this amplitude and that is very minor. There's one little Fourier transform we have to do. And the corrections, everything that's contained in here, to the first power 32 pi g, these kappas are related to Newton's constant. All the corrections to all orders in velocity, remember Feynman diagrams are relativistic, all orders in velocity is contained in here. And if you want to continue the perturbation theory, classical perturbation theory, and you want the next corrections, what you do is you have to go to higher orders. If you count your kappas, you'll see this is order g square. This is order g. This would be called first post-Minkowskian. And this would be second. It's just an expansion in G. Order by order in G, we will correct the Newtonian potential. And it comes directly from the concept of this being a spin-2 particle. That's all you need to know. And from the effective field theory, well, I didn't talk about this, but what's the coupling and what's the operators and what are you supposed to do? Lowest dimension operator. That's the dominant one. Higher dimension operators, that has to do with tidal effects. So there's a whole organization that's universal, and you've heard it in all the talks about how to organize things in terms of operators and how to be thinking about separation of scales and how to apply field theory to many problems where you would not imagine you could do field theory. Okay?
The reason that you don't talk about post-Newtonian because formally you're including all post-Newtonian.
No.
Not expanding in V over C or
so post-Newtonian. Okay. Post-Newtonian is an expansion in G and V square. This is what we call post-Minkowskian, is an expansion in G. So the reason why you'd be interested in this, well, for example, right now at LIGO, post-Minkowskian is not terribly interesting. And the reason is because the only thing LIGO can see is circular orbits. And the reason why it can only see circular orbits is because the gravitational radiation circularizes the orbit. By the time you have a signal that's loud enough to hear at LIGO, the orbit is circular. And then, if you remember your circular orbits, G and V square are tied, right? Same energy, potential, and the virial theorem. But if you have a different kind of orbit, like a highly elliptical one, which will be a much weaker signal because the signal becomes strong once it's radiated enough and the distances are close enough so that you can actually detect something with today's detectors. The orbit is circular. We just have to wait another 10 years, much, much more powerful detectors, and then elliptical orbits will be detectable. And then you would like to have information also higher order in velocity. So that's, you could say, the motivation. This is why Damour, Bonanno, those people are thinking, we need to be thinking now post-Minkowskian, not just post-Newtonian. Now, the way this is related is you can take any result here and series expand to the proper order and velocity, then the two should be identical. Yeah. Now, the post-Newtonian, you could say, is ahead of us in powers of g because the velocity expansion helps you calculate. But these two travel together. They're interlocked. You can gain information from one to the other. But anyway, we who do field theory, we will definitely want to do all orders in velocity because why would anyone not want to do it relativistically, right? That's what we do for a living. Everything is relativistic. Quantum field theory, our very thought patterns are relativistic. So we're going to keep all orders in velocity. Okay? And that's what we will calculate. We will calculate the corrections to this, all orders in velocity. Okay? Now, before we do the case of general relativity, let's do electromagnetism. Because what's the difference between gravity and electromagnetism? Can anyone tell me? Like the real difference. Well, spin one, spin two, right? So the problems are identical from our point of view, right? We're just doing Feynman diagrams. So if we want electromagnetism, make this spin one, don't make it spin two. So if you want to do spin two, let's just do a warm-up with spin one. It'll be the same problem. It'll be two copies. We're going to use the double copy to get gravity. Okay, so let me remind you how to do this. So, okay, here's Coulomb, Q1, Q2, 16 pi r. And, okay, there's a plus sign here. In some units, anyway, I'm not sure what units these are, but anyway, some units of how you want to define the charge. And the place my definition of my normalization comes from is I want to normalize it that my interaction between the scalar particle, the spinless particle, and a photon, is a photon. I want this to be IQ, P1 minus P2, and this is 1 and 2, and this is my photon. Oh, with a mu here. Mu and a mu. Okay, there's a photon there. That's the Lorentz index of the photon. Okay? And then I need a Feynman propagator. Okay, so I'm going to pick a gauge. Well, we'll get rid of that in a second. If we try Feynman gauge, minus I eta mu nu over p squared if p goes this way. And what else do I need to know? Well, I need to know, this will be very useful for us, I need to know how to do a state sum of the polarization vector. So this is minus eta mu nu minus p mu. This is the photon momentum, p mu. Make this L. L nu, P nu, L mu, and then P dot L. And this is known as a reference momentum. They both satisfy P square equals 0, Q square, L square, let me erase well, L square equals 0. The reason why there's this reference momentum is because these photon polarizations, two physical states, and that's exactly what this thing does. It removes two physical states. There's two conditions. Epsilon dot P is equal to 0, and then epsilon dot L is equal to 0. That removes two states. Okay? And this thing is the physical state projector. Let's call it P mu nu. Okay? And then what we want to do is now go ahead and calculate the scattering amplitude of two scalar particles through a photon. Okay? So I can do it by Feynman rules. We'll get slicker when we get to gravity. But we can just do it by Feynman rules. So I, Q1, oh, let me draw my Feynman diagram with labels. So that's 2 and 3 and 4 and 1. I'm going to use an all outgoing convention. All the momenta are going out. P1 minus P4, mu minus I over T. T will be, let's make this Q. T is going to be equal to Q squared. That's an I, looks like an L, but that's an I. And then I can have two propagators. Maybe this is Feynman gauge. I can also pick light cone gauge. Let me pick light cone gauge. Light cone gauge has that physical state projector. Q mu L nu plus Q nu L mu divided by Q dot L. This is the reference momentum. Let me close that, and then I Q2 P2 minus P3. Now, and there's nu here. Now the first thing that's very important is this thing, or I should say like this thing, is a conserved current. And a conserved current satisfies Q mu into this has to be 0, or Q nu into that has to be 0. Okay? And indeed, we can check that. So let's look at that. P2, so Q nu, let's say Q nu, where am I? Q nu into P2 minus P3 nu. That's equal to P2 plus P3. So Q, reverse that so that my sign is right. So that's P2 plus P3, P2 minus P3, and that of course is equal to P2 square P2 square minus P3 square, which is equal to M square minus M square, which is equal to 0. So the current is conserved, okay? And what that means is that the same argument works the other way. So what that means is that this thing is irrelevant. That doesn't count. Okay, now there's a reason why I'm doing this a little slowly. It's because we're going to do the same in gravity. Gravity is more complicated. Once we see how it works in electromagnetism, we'll just copy what we understand from electromagnetism, and we'll do the same in gravity. Yeah. Okay, so there we have it. The only thing that survives is this, the eta, and this. So I need to work out what is P1 minus P4 dotted into P2 minus P3. And that's equal to, there's, my twos. Well, anyway, if this thing is P1 dot P2, and then P1 dot P3 minus P1 dot P3, and we can just work this out. Minus P1 P2 dot P4, and then P plus P3 dot P4, and then what you do is you say, oh yeah, there's some momentum conservation. P1 dot P2 is equal to P3 dot P4, and P2 dot P4 is equal to P1 dot P3, and then we can write also that 2P1 dot P3 is equal to T. I think I need another marker. Is equal to T, there's my T, T is Q squared, is P2 plus P3 squared. That's what T is. T minus, let's see, where was I? T plus, it's minus T minus 2P1 dot P2. Okay, so I did a little bit of algebra. Anyway, where are we? This thing, you do that little bit of algebra for P1 dot P2 plus T. Now, there's a reason why I'm kind of working it out, because we're almost at the answer of that we're looking at, that we want. So the answer for the amplitude, using that Feynman rule, it's I Q1 Q2 for P1 dot P2 divided by T plus 1. Okay? Now we want the potential. Now, the potential, we can think of that as extracting it from an effective field theory. There it is. So you can think of it as this Feynman diagram. The potential, notice Fourier transformed in momentum space, is this Feynman diagram according to the effective field theory that I mentioned in my more general lecture of how we extract potentials by writing down an effective field theory based on potentials. And we match this to that. The matching is stupid because it's the same as my matching. This is that, right? Now, there's one little detail which I'm going to gloss over, but you can consult your quantum mechanics books or non-relativistic quantum field theory books, the normalization of states and how you define the potential. We have to actually change the normalization to get the potential, the normal one, Newton. We have to take care of some normalization. You may remember maybe undergraduate, maybe the graduate field theory. There's something about normalization of states. There's a non-relativistic normalization, not the one we're using with the Feynman diagrams. So the non-relativistic normalization, there's a 1 over I. The 1 over I, well, first of all, this I You know, there's some, this I doesn't belong. That was put there by Feynman because Feynman, you know, had his conventions from the path integral. So let's get rid of that 1 over I. We definitely don't want an imaginary answer. And then there's also 1 over 2, the square root of the energies. So this is energy. And that's for each one of these 4 external legs. Okay? And if you let me gloss over that point, then we're good to go because we now have the potential. But we have it Fourier transform. So in order to connect to Newton, we just have to do the Fourier transform. So let's go ahead and do that. First thing we should do is go to center of mass coordinates, right? Because normally you're going to write a potential that looks like this. The R, that's the distance separation. And normally, of course, we work in center of mass coordinates. There's P. P would be the spatial component of either P1 or P2 in the center of mass coordinates. So let's pick, okay, so this is what we're after, V of R and P. So it's the Fourier transform. Let me write it as P and R to match what I have above. P and R. Okay?
Question?
Yeah.
Yesterday you mentioned that it's non-local.
Yes.
Does that have to do with the fact that you're choosing a frame?
No, it has to do with the fact there's a 1 over T here. That's all I mean. So when you match, that thing is non-local because it matches, and you need the 1 over T in there. And you can't escape the fact, no matter how you twist and turn, you can't escape the fact that it's a long distance 1 over R potential, 1 over R, which you have to match the Fourier transform. It's just the 1 over R that'll match the 1 over T after the Fourier transform. And it's in there for the completely stupid reason. If I say this is that, up to the normalization, there's my 1 over T. Okay. So we want to go to center of mass reference frame because what else would you do? So we take that P1 is equal to E1 and P2 is equal to E2 and minus P. Okay? And then we have these on-shell conditions, right? At least in the scattering amplitude, there are on-shell conditions. So P1 square has to be equal to P1 minus Q squared has to be equal to M1 square. Okay? And this actually puts a non-trivial constraint. So from here, I can deduce that P1 square is equal to P1 square minus 2 P1 dot Q plus Q square. So therefore, I get that 2 P1 dot Q is equal to Q square. Okay, and I can go through the same argument looking now at P2. P2 square has to be equal to P2 plus Q, and that's equal to M2 square. I go through the same thing, and I get that 2P2 dot Q has to be equal to minus Q square. Okay? And now we look at the center of mass, and what's the solution for this? If we put this together, we have that what solves this is Q is equal to 0 in Q. So this is a solution. This solves these equations. See, if I want P1 dot Q and P2 dot Q is equal to Q square, and you see I can solve that by coming here. So you ignore the energy. So then what you get is, so the energy dotted into Q, that's 0. There's the P into Q. And then there's minus P into Q. So I get the right minus sign. Okay? Now, I'm almost done. In this setup, what I have is that V of P and R is equal to just the Fourier transform d cubed q, 2 pi cubed, e to the I q dot r, oops, q dot r, and then V of P and Q. And I can put arrows on them. Yeah. And that's my answer for the potential. Now, if you're watching very carefully, there's a little sleight of hand here. So right here, we have on-shell conditions. In fact, I was using it right here. They all on-shell. What on-shell conditions do I have in a potential? None. So what I did is I took an off-shell continuation. There's a specific choice made here. Right? I'm here, I have this constraint. There, I don't have any constraint. What constraint? I don't see that constraint. There's no p squared equals m squared type constraint. In fact, this is three-dimensional. There's a choice made here. I snuck it in while you weren't looking. This thing is ambiguous. This is not unique. Now you say, oh, well, that's weird. But suppose I gave you a Hamiltonian. In fact, this is what our Hamiltonian will look like. We're going to make it relativistic, so it'll be p squared plus m1 squared, square root, and then plus p squared plus m2 squared plus v and p and q. Is this potential unique? Do you remember something in Hamiltonian mechanics? Canonical transformations? What happens if I make a canonical transformation to that Hamiltonian? Will my potential be invariant? No, it's going to change. That's actually the same ambiguity. That's not an obvious statement, but nevertheless, it's a true statement. What this potential does for a living, it's ambiguous, but what it does is if you reverse the process, you fed this into our effective field theory, and you worked out the scattering amplitude from our effective field theory based on the potential, you'd get the correct scattering amplitude. That's the matching. And the claim is that once you have done that, you now have a perfectly valid potential that you can then use for whatever physics you like, and all those differences need to drop out. Now, is that really true? Of course, you can check it. You can be sure we check it. Every time we do a calculation, you get a potential. Suppose we had done something a little differently about how we use these on-shell conditions, right? Because you can take m squared, replace it with p squared, back and forth. Depending on exactly how we do things, maybe you get, or not maybe, you definitely get different answers. And then you can check its equivalent to a canonical transformation. Yeah. But nevertheless, we have a potential. Let's go inspect it. Okay. Now, okay, we have to do a Fourier transform integral. Well, that Fourier transform integral, well, there's two of them. This is t is equal to minus q vector square. See, I'm looking at this solution here. So I need to know how to Fourier transform 1 over q squared. I need to know how to Fourier transform 1. I think 1 we know. This place is famous for some guy that tells you what the answer, right? It's the delta function. The other one, well, it's pretty simple. Integral d cubed q. So you can look this up or do it do it however you want to do it. E to the I q dot r, 1 over q squared, that's equal to 1 over 4 pi r. Sounds like we're heading in the right direction, aren't we? 1 over r. I've seen that over there. Newton said something about that, right? 1 over r. So, I am almost done. I now have a potential. Okay. I now have a potential V of P and R after the Fourier transform is equal to Q1, Q2. There's 4 E1, E2. This is from the non-relativistic normalization, the 4 E1, E2. So remember, we use the on-shell conditions. So the energy of this particle and the energy of that particle, same particle, is actually identical because we're in the center of mass reference frame. So the momentum is P and minus P. Whoops, I'm sorry, sorry, I said that wrong. The momentum is P and the momentum is still P, but at a different angle. So the energy is identical. Okay, center of mass frame. So it's a square root from each one, and then put 4 of them together and use the fact that they're identical in pairs. That's where this normalization comes from. And then I put in, where was it? I had it somewhere here. Where did I have the amplitude? Ah, there. P1, P2. I need that. There's a P1 dot P2. 4 pi r delta cubed of r. Okay. And this just corresponds, of course, to this, and the delta function corresponds to that. Now I look at that and say, what happens if I go to the static limit? Static limit. That's the only thing Coulomb knew. Coulomb didn't understand, of course, if there's velocities involved. So we should go to the static limit if we want to look at Coulomb. So we have that P1 dot P2 divided by E1, E2 is equal to E1, E2 plus, I guess, P squared, but I said it's static, 0. This is static. No velocity. Okay, and I'm supposed to divide by E1, E2. So this thing goes to 1, and I think we know the answer. Q1, Q2, and if I didn't mess up my factors of 2, I get 16 pi r plus velocity. Velocity. Corrections. Okay, so what we have here, this formula, this formula is the correction of this one. Well, I meant to say ignore, because we're talking about 2 point charges or 2 charges that don't have to be points but far enough separated. If they're far enough separated, no delta function, right? So the delta function only counts if you're actually touching. But okay, these are points, they're obviously never going to touch, so forget about that. And remember separation of scales. So this can never be, this is not part of our problem. Our problem is 2 point charges separated. Okay. So this is the relativistic correction to this. in special relativity, if you want to know to the potential to the first order in these charges, this is the complete answer, derived from Feynman diagrams. And the part that I think you should be impressed with is the only thing we used is spin 1 right here. Massless spin 1. Nothing else was used in this. And this, you think, well, it's quantum field theory. What does it have to do with classical physics? The answer is everything, because the potential lives right here. This gives us that potential. And once we have the potential, we have the Hamiltonian. There's, see? I now have, let's make this R. Now it's R. I now have a Hamiltonian. If I have a Hamiltonian, I can do any classical physics I like, valid to this order of perturbation theory. Yeah. So let's do gravity. So that was a nice warm-up. How do we do gravity? Well, we could say, well, Einstein and general covariance. No, of course, we're not going to say that. What we're going to say is spin 2. Okay? And then we're going to say something else while we're at it. We want this to be spin 2, and we don't want the delta function, because the delta function is not interesting. It's not part of our problem. Right? That's where the two black holes are touching. That's not what we're interested in. So in order to get not a delta function, I need the propagator. If I need the propagator, that means I'm on the residue of that pole, or you could think of it, I need the propagator. So effectively, this thing is on shell. This thing, this guy is effectively on shell, at least for the determining the potential. Very shortly, see, so in the beginning it's on shell, but somewhere I went off shell right here. See, when I take the Fourier transform, I go off shell. But the key contribution, the only contribution I am interested in, where was it? It was right here. That's it. I need that pole. Anything without a pole I can ignore. And that's very cool because it means it's effectively on shell. I can take t goes to 0 because I'm not interested in I'm only interested in the singular part of t. I'm not interested in that. If I take t goes to 0, then effectively I'm on shell. And that means that I can now start doing it by putting this on shell in the middle. If I put it on shell, I guess you came to my lecture and you heard something about how do I get a graviton vertex? What's the graviton vertex? I'm going to convert this to a graviton vertex. So get rid of this. So I'll leave the same diagram. I will put in a mu and a nu. And then I will put in, better get rid of that charge. I will put in a coupling, kappa. And then P1 minus P2 nu. That's our friend, the double copy. See? 2 copies. Just took 2 copies. And I'm just going to use that. And this thing is, of course, gauge invariant. Why is it gauge invariant? Because one of these is gauge invariant. 2 of them are also gauge invariant. There's one more condition I need to impose. Gravitons are traceless. I need to impose, well, I'm going to impose the following. So epsilon mu nu, so this is the polarization tensor of a spin 2 particle, massless spin 2, the graviton. I need to impose, well, first thing I'm going to do is write it as 2 copies. There, it's a product. each one has to be gauge invariant. There has to be a symmetry. If I replace one with the other, it better not change the answer. And I have to impose, epsilon mu nu equals epsilon nu mu. I have to impose epsilon mu mu equals 0. Remember, gravitons are traceless. What is that trace? The trace is actually a physical particle, but not in our universe. There's a universe elsewhere that has a dilaton that changes like a fifth force, and that would be the trace. But our universe doesn't have that, so we have to impose that. Okay? So now let's go ahead and calculate the so first, let's see, a 3-point amplitude. Well, there it is. I can maybe clean it up slightly because epsilon dot q equals 0. This is q. So let me just do this as a double copy. Oops. Yeah, sorry about that. Okay. So what I'm going to do is take a 3-point, 3-point, and a 3-point. And there's a sewing I need to do. I have a sum over states. I have to do this state sum in that diagram. That state sum, epsilon mu nu, epsilon rho sigma. So let's make it rho sigma. And then I have to sum over the physical states crossing there. And there'll be a star there. And that, let me write it out. It's a little more complicated. So this p mu nu, let's define that to be eta mu nu. This is the projector from the photons. L mu q nu divided by p dot L. So this is the physical state projector, although I think I flipped the sign, but that doesn't matter. So that's equal to p mu rho, p nu sigma. So this gets home to that. P mu rho, p nu sigma. And I have to symmetrize it. Gravitons are traceless symmetric tensors. So I got to symmetrize. And then plus would be p nu rho, and then p mu sigma, and then I have to remove the trace, minus 1 over d minus 2. And the trace would be p mu nu, p rho sigma, whoops. So this p is a projector, p rho sigma. Okay, so what's the first thing that happens? So you notice there's all this stuff. What's this stuff going to do? Anyone want to venture a guess? Yeah, I see someone saying out the window. Yes. This thing goes to 0. Why? Because these are conserved currents. How do I know it's conserved currents? Because it's built out of these two conserved currents. It's kind of trivial.
Is that the most general coupling of a scalar to a graviton?
No, that's the minimal. That's the most general minimal coupling, which I don't know how general that is, since it's minimal. You know, it's essentially unique, or it's unique here. Yeah. So it's you know, the effective field theory is our guide of what we're doing. Right? We're writing down the lowest dimension operators hidden away in there. Okay. Plus, if you ever get confused about which operator, you know we're allowed to cheat. So even though I say we don't like Einstein, we're allowed to look and see exactly what the Einstein vertex is and confirm exactly what I said, that the graviton vertex, right, you start from the Einstein action, expand it out, get the 3 vertex, the Feynman rules, put the legs on shell. This is what it is. Yeah.
Elaborate a little bit on the on-shell.
Yes. So this is.
Yes, so this satisfies p squared, p1 squared equals m1 squared. This thing satisfies q squared equals 0. I'm computing, the thing that's unusual about what I'm doing here is normally in a Feynman rule, this is an off-shell leg, right? An off-shell leg means that the diagram can, in general, be gauge dependent. The individual diagrams can be gauge dependent. Here, because we are only interested in the 1/t pole, because we want the long distance, this goes on shell, so q squared is equal to 0, p1 squared equals 0. Whoops, this is p4. I've reversed 1, 2. Well, oh, I see what I've done. Let's call this 2 and 3, 2 and 3, and this is 1 and 4. So everybody's on shell. You see a particle, it's on shell. Okay? And it's gauge invariant because it's built out of gauge invariant pieces.
So this is going to be like analytically continued to non-zero t, or?
Yes, and the spot we are going to do that is right here. We're going to somewhere, we're working away, we're going to calculate something like this, right? We're going to ignore this. And around here, there's on-shell conditions. And then the next step, we're going to say, oh, let's go off-shell Fourier transform. Okay? And the pieces you're losing, the pieces you've lost control of, would be delta function. So we're not interested. And other pieces we've lost control of are unphysical pieces that are equivalent by canonical transformation. Okay, okay, so where are we? Ah, yes, the double copy. So this is irrelevant. So you see the eta mu nu? So the eta mu nu, it's just sewing copies of the electromagnetism. One electromagnetism is getting sewn, another electromagnetism. One electromagnetism, but I swapped who mu and nu are, but it's the same thing. And another one. This thing is a subtraction of something. So we can, let's look at our diagram. So this is equal to minus I, the sum over states, and the state sum is this one, the one I'm showing on the now it's graviton. The graviton is this, so that's the state sum, this I throw away, so it's just a bunch of eta mu nu, so you just have to contract, I'll write this P2 dot epsilon squared. Oh, there's some factors of 2. Oh, I know what happened to the 2's. Probably should have been a cap over 2. Probably a cap over. And there's some, okay, never mind the normalization. There's some 2's I have to take care of. Okay, then 1 over q squared. And then P1, and this would be epsilon of that. And then I have P1 dot epsilon, okay, it's star because you're reversing incoming and outgoing on this leg. And here's the formula, the P mu nus or eta mu nus. So the answer is very simple. The answer is, this is equal to minus I, the sum over states. Okay, wait, all right, let me do this. Sorry, I'm going to do the state sum And so that's equal to, well, let's see, there's an eta, like a P2, and then this becomes an eta that contracts P1 to P2. Okay, there's 2 copies of them. So I have to square it. There's my 1 over q squared. Let me call that t. T is equal to q squared. But then there's this term here, 1 over d minus 2, take out the trace. If I trace it, this thing, see? So this is now contracted to itself. The P2 becomes contracted to itself because the mu and nu refer to the 2 guys you see here. So I get P2 squared, that's M2 squared, M1 squared. So the thing I have to subtract out, 1 over d minus 2. I get M1 squared, M2 squared. And there we have it. Okay, we're almost done. Right? That is the potential Fourier transformed. It's the potential. Oh, I lost. Sorry, I put the 1 over t. I lost. Let me put it out in front. There's a 1 over t here as well, right? See, the 1 over t. It was just sitting in front of this whole thing, and there's a bunch of contractions. Okay. Okay. So. Yeah.
Q2 is like has originally 2 indices or 1 index? This is
1 index because I used here. Yeah. See, I'm literally factorizing. So if I now take this vertex and I contract into epsilon mu nu, then it becomes like this. This is vector. Yeah. Literally factorizes. Okay. So now what do we do? Yes. Well, we want to ignore or drop. I anyway dropped it already. Drop q to the 0 and beyond. So anything without this 1 over q squared, I'm not interested in that. That's some contact term. The delta function, by the contact term, this thing, I'm not interested in that. The next thing I do is non-relativistic normalization. Whatever I did to do Coulomb, I just do the same here, yeah?
Is that supposed to be just an M2 or an M2?
Square, sorry. Whoops, thank you. Let's get rid of that. Oh, then I guess we live in 4 dimensions. I better do that. D equals 4. And then I want to take, following the discussion before, I want to take, go to the center of mass, center of mass coordinate system. I want q squared equals minus q squared. And then I want to take the Fourier transform. All right? So this thing up to the normalization, it's this. I have to include the non-relativistic normalization, and that gives me V of P and Q. So 1 over 4 E1, E2, and then this thing. well, maybe let me write it out. Times this thing. So if I'm careful with my signs, which I'm not sure if I was, but this gives V of P and R is the Fourier transform of well, let me divide this by I. It's a Fourier transform of this object, this times that. I should have put in a kappa square in here. Kappa square. And then 4 E1, E2, integral d cubed q, 2 pi cubed, e to the I q dot r. Oh, yeah. E to the I, it's the same thing I did in QED. I'm just doing it in gravity. Divided by minus q square, P1 dot P2 minus a half M1 square the 1/2 4 minus 2 minus a half M1 square M2 square. Okay. And that Fourier transform is the same one. It's the same Fourier transform, of course. So there you have it. V of P and R is equal to minus kappa square 32 pi over R 2 P1 dot P2 divided by E1 E2 minus M1 square M2 square divided by E1 E2. Square. Whoops, square. Very important. Yes. Just copy from here. Like Fernando said, there was a square missing. Oh, I see why the square was missing. It's missing here as well. Okay. So, okay, let's see, what is this thing? So, of course, we want to verify that we get Newton. So we have to go to the static limit. So let's go to the static limit. Static limit. So it's the same thing. P1 is equal to M1, 0. P2 is equal to M2, 0. And E1 is equal to M1, E2 is equal to M2. That's the static limit. So, see, it's very nice. So this just turns into M's. Oh, here. This just turns into M's, M1, M2. There's a 2 minus 1. The E's turn into M's. So the final answer is the potential calculated straight from the scattering amplitude is V, and let's call it static. V of R is equal to minus kappa square over 32 pi R M1 M2. At which point I can recognize it and say, oh, I know what that is. I just have to do one little tiny thing. What is this kappa square stuff? So kappa square over 32 pi, that of course has to be equal to Newton's constant. Okay? So that verifies, this verifies Newton's constant. One little tiny difference, this formula, that's a cool formula because this formula is the potential of two black holes orbiting each other, now corrected by general relativity, by special relativity. I guess also general relativity, but it's one power in general relativity, one power in Newton's constant, all orders in velocity. So it's the relativistic correction to this order of perturbation theory. Oh, let's fix that. I don't like that kappa. There we go. Oh, the pi. I should eat the pi, right? Pi. There we go. So that's an improved formula. It wasn't very hard to work out. And I think you should be very impressed at the short distance, like I got it on the blackboard. Right now I'm doing general relativity. I got it on the blackboard from the starting